Hey guys, so I'm not really going to be whispering. I'm just going to be talking as softly as I can, basically. I'm just going to be flipping through this book. It's an astronomy book. It's a little dusty. I don't like dust covers. I think they make the books kind of awkward to open and read. And I don't mind the look of just a plain book instead of a nice printed cover. This is just a picture of, I think, the Milky Way galaxy as seen from Earth. Could be an artist rendition of another galaxy, though. But I'm pretty sure it's the Milky Way. Here's the title page. It's got a picture of an astronaut's boot print on the moon. It's actually a very famous picture. I don't remember which mission it was taken from. This is an artist rendition of the Voyager 2 spacecraft, presumably far in the future as it's passing by some kind of nebula. This first section of the book mostly covers the history of astronomy and all the important figures in it. Like, here we have Aristotle, who he thought the Earth was the center of the universe. But at about 350 before the Common Era, he did know that the Earth was round and it was a sphere. I think, yeah, he knew because he saw the shadow of the Earth on the moon. This isn't a guy as well known as Aristotle. I'm not sure if I can pronounce his name properly. Aristarchus of Samos. Just a little while after Aristotle. He was possibly the first person to think that the sun was the center of the solar system. Alright, I guess the universe in this case, but they didn't really understand how large the universe was. he also thought, or I suppose hypothesized that the stars were very far away because they didn't move. Hipparchus of Nicaea, about 150 years before the Common Era. Sorry, I'm still getting used to hearing myself in my headphones. He discovered that the orbit of the Earth, or the axis, I should say, wobbled. The axis that the Earth rotates on, shown here, is offset. It's tilted a little bit, and that's what causes the seasons. He actually, he managed to calculate. I'm sorry, I'm getting ahead of myself here. He realized that it was tilted, and there's an effect on spinning objects with tilted axes called precession, where the object will spin, and then at a different rate the axis will also spin. It's called gyroscopic precession. And he discovered that applied to the Earth as well. He actually managed to calculate a fairly accurate period for how long that rotation took. And it says here, he actually doesn't say what he calculated, but it says the period is about 26,000 years. He also calculated the length of a year to within just a couple minutes. Not bad for almost 2,200 years ago. This here is Ptolemy. It starts with a P, but it's silent. He came up with an idea that turned out not to be very accurate. It was the idea of epicycles, and what that was is as the orbits of the planets, as the planets orbit the sun, they went in circles. If I remember this, he came up with this to explain retrograde motion, because the Earth orbits at a different speed than the other planets do. They sometimes appear to go backwards. You'll get, if you watch a planet in the sky over a period of time, it'll go like this. And that's called retrograde motion. It does a zigzag or a loop, something like that. And that's caused by the planets orbiting at different rates. And he came up with these epicycles to explain that, because I believe he thought the Earth was still the center of the solar system. But the epicycles model was actually quite complicated, and it, well, it wasn't right or very useful. Here's Copernicus, who most of you have probably heard of. He proposed the heliocentric model of, again, I want to say solar system, but it was probably the whole universe. Heliocentric meaning that the sun is at the center. But his model had circular orbits, meaning perfectly circular, which is not accurate. They're ellipses, so they're elongated. Almost every orbit is slightly elliptical. And so it couldn't 100% accurately predict the location of planets. This guy, I'm not really sure how to pronounce his last name. I guess it's Tycho Brahe or Tycho Brahe. He was basically from a very rich family. He had a lot of money, and his interest in astronomy let him spend a lot of time doing astronomy, basically. So what he did was he basically measured everything much more accurately than had been measured before. But he still liked the idea of a geocentric model, meaning that the Earth is in the center. It was very hard to get people to stop thinking the Earth was the center of the universe. That's just what people believed. It seemed common sense at the time. He had, here I think the next page, here's some models really briefly. I don't know if you can see them in enough detail though. A is Ptolemy's model, where the Earth was in the center, the moon orbiting it, and all the planets and the sun orbiting it. Now this isn't actually completely accurate because it doesn't have the epicycles in it. But that's the idea, basically. These are just general models. This is the Copernicus model, where the sun is at the center. And obviously there's circular orbits. This is the most accurate here. For diagram purposes, this is actually, it's fine. I've just Saturn at least. This is Tycho's model, where you had, oh yeah, okay, sorry, I made a mistake. He thought the planets orbited the sun, but then the sun orbited the Earth, which I guess still sort of means it's the center of the universe or the solar system. Though, to be honest, I feel like you'd have to make a bit of a logical leap to assume that all the planets orbit the sun except the Earth. But I suppose the idea that the Earth is special was, and still is, kind of prevalent. And it is special. Just not in that kind of way. This guy is Johannes Kepler. He's pretty important. He came up with Kepler's laws of planetary motion. And they're accurate. They're one of the first, I guess, ideas here that still applies and works. It explains, or doesn't explain, but it describes elliptical orbit motion. And he was actually Tycho's assistant. He used Tycho's very accurate measurements in order to come up with his 3 laws. Excuse me. I'm just gonna have a drink. So that brings us to Galileo Galilei. Again, I'm sure you've all heard of him. He used the first refraction telescope to do astronomy. I feel like I've started talking quieter. Anyway. Something interesting that he did was discover sunspots, and in turn that the sun rotates, because you could watch it over time and see that the spots rotated with it. If I recall, the way he did that was actually using his telescope, or some method of refraction, to project the sun onto a sheet when it was very close to the horizon. And when the sun's very close to the horizon, you can look at it without necessarily damaging your eyes and get a bit of a clearer image that's not as oversaturated or overexposed, I guess you could say. Oh, you know what? He also, with his telescope, he was the first person to discover that Jupiter had moons. He didn't discover all of them. Jupiter has something like 60 moons on it, or around it, I should say. But he discovered a couple of them, and they are now still called the Galilean moons, in honor of him, of course. I think the last one I'm going to talk about is Newton here. Obviously, just about everyone's heard of Newton. If you took any kind of math or science in high school, honestly, the majority of the stuff you learned was probably developed by Newton in some way or another. He is the father of physics. He effectively created the entire field. And I actually don't know how much astronomy he did. I'm more of a physics enthusiast, but he did obviously develop the theory of gravity. You've all heard the famous story where the apple fell and he went eureka, which I don't believe actually happened, but whatever. He also invented calculus, basically to help explain how the elliptical orbits worked and why Kepler's laws explained them. To be fair, though, he developed them at the same time as Leibniz, who I think is a mathematician. Well, I'm assuming if he also invented calculus, but and as much as I love Newton when doing calculus, I prefer Leibniz notation. I think it's a little bit more useful. Let's continue on. Here's a little diagram of the Doppler effect, which I like. It basically explains why a police or a fire truck siren sounds like it's a bit higher when the truck is driving towards you, and lower when the truck is driving away, because the waves, the sound waves, or in this case, the electromagnetic light waves, get stretched out or compressed. Here's another picture, I think, of Voyager. Not a photo, obviously, just a painting or drawing. See, now, this is kind of interesting. I don't remember some of the specifics from a course I took on basically stars and galaxies. But I think this is the same kind of graph that denotes the main sequence. This being the main sequence, or what you would call main sequence stars. Up here are stars that are very bright and burn very hot, and down here are stars that are cold, relatively speaking, and are very dim. Stars, I can't remember where they start, actually, but they move along the sequence. I think that they go up, but I could be wrong. Let's see. Yeah, that's not helping. So, don't quote me on that. I could have it wrong. It's been a while. But basically, stars start dying and they diverge from this sequence. So they'll go up here and become supergiants, like these enormous stars here. And then they'll die and go supernova and collapse on themselves, and then become white dwarfs or neutron stars down here. This star, the big one in the corner here, is an interesting one. It's called Betelgeuse, and you've probably seen it. It's part of the constellation Orion. It's his right shoulder, so it's on the left. It's a very, very large star that's close to the end of its life cycle, and hopefully, if we're lucky, in our lifetimes it will go supernova. But because the lives of stars are so long, it being close to the end of its life could still mean that's thousands of years away. But in all likelihood, because of how far away it is and how long it takes the light to reach us, it's already actually died. But when it goes supernova, for a time, the individual star could be about as bright as the moon, and you'd be able to see it during the day. I think it would be very cool if that were to happen. I'm probably going to gloss over a lot of this. I can't remember a lot of specific information about individual planets. Except that this is not to scale at all. I can go over a couple things about the sun. One of the facts I always liked about the sun is the fusion that takes place produces electromagnetic energy, or radiation, I guess I could say. And you've probably all heard the famous equation E equals mc squared. And that's basically just saying how much energy you can get out of a bit of mass by turning it into energy completely. And the amount of energy the sun turns, or the amount of mass that the sun turns into energy every second, is about 11 million tons, approximately, which is a lot. I think it's just kind of cool to think about how massive that amount of energy is. If you look at a nuclear bomb, the amount of energy gotten out of the mass, gotten isn't a word, I don't think, is enormous, but the amount of mass used up is minuscule. I don't remember the percentage of mass converted to energy in that reaction, but it's very small. It's only a couple percent. Something I think is neat is the temperatures of the different sections of the sun. The core is, it's on the order of about, it says 15.6 million degrees Celsius, but it's on the order of 15 to 20 or so, around there. And as it goes out, that decreases, of course, and the surface is actually only about 6,000 degrees Celsius, which is still hot enough to melt any substance known to man, but it's, I feel like it's not as hot as you would think. Like, we see temperatures of over 6,000 degrees Celsius on Earth all the time. The air around a lightning bolt is significantly hotter than that, only for a split second though. Oh, but then the interesting part, or the part I wanted to get to, is that here, this bit around the sun is called the corona, and it actually extends out much farther than the actual sun, or than it's shown here. I think it goes out about 1 or 2 million kilometers. The sun is about 1.5 million kilometers. And what's interesting is that the temperature of the corona is actually about 2 million degrees, which is significantly hotter than the surface. During an eclipse, a solar eclipse, you see people warning against looking at it without eye protection, and they'll sell little cardboard, almost like 3D glasses, but they just have protective lenses in them. The reason for that is when the moon blocks out the sun, it blocks out the majority of the visible light, which means that your eyes adjust to the dark, and your pupil opens to let in more light. And if you look at the sun, because the corona is so hot and it extends out past where the moon blocks, the hotter something is, the more energy the radiation coming off of it has. So, whereas here you get a lot of light or radiation in the visible spectrum, out here you get a lot of light in the X-ray and ultraviolet spectrum. So if you look at the sun during an eclipse with no eye protection, you get significantly more ultraviolet radiation than if you were looking at it during a bright sunny day, because your pupil is letting in a lot more of it. It's like when people warn you against looking at the sun, but you can damage your eye much faster. Just a little diagram of the electromagnetic spectrum. Here's the corona, or at least the explanation of it. And a nice little picture. The ejected matter is it follows turbulent magnetic fields. These are the ones I'm probably going to mostly skip over. Oh, but there's a... Sorry, I reached my maximum record time. And realized that I may have accidentally filmed the first half of this half-hour video, the first half hour of this video in portrait mode, which would be the worst thing ever. I don't know if I can rotate videos, we'll find out. Oh. What's the thing about Jupiter I wanted to talk about not here? No, it's not. That must be in another part of the book. But just in case you weren't aware, there's a big spot on Jupiter. You can't see in this picture, but you can see it right here. And it's a big storm that's been going on for hundreds of years. And the storm is approximately the size of the entire Earth. And like Jupiter, I think the patterns in the atmosphere look like one of those sand art bottles. Right before you shake it too much and it turns brown, like always happens. Oh, Uranus has an interesting feature. It rotates perpendicular to the orbit, like if you're looking at the solar system from above, the sun is in the middle, the planets orbit it. Most planets rotate in the same orientation of the orbit. Uranus rotates at a 90-degree angle to that. Oh. I'll talk about that some other time. Neptune. Poor Pluto. Not a planet anymore. This book is clearly outdated. Oh, this must be where the Jupiter thing I wanted to talk about is. Debris in the solar system. Oh yeah, it's right here. This is a comet called Shoemaker-Levy. Shoemaker-Levy 9, actually. And we learned a lot about comets from this, because as it was drawn into Jupiter's gravity, it broke apart. You can see all the little pieces here. About 20 of them, it says. And the reason that happened is because when it was falling into Jupiter, because of the gravity, it was ripped apart by what's called tidal forces. And I'm just going to use a prop here to briefly explain that. Here, a Sharpie will work. If Jupiter is here, and this Sharpie is being pulled in by the gravity decreases the farther out you get. So over in fields of strong gravity, when you're near the source, that's very noticeable. And what happens is the front here feels a much greater force than the back. So the front gets pulled in faster. And if something is not very strong and big enough, it can get ripped apart. In the case of black holes, you can get so close to them, and the gravity is so strong that this happens very extremely, and you get the proper term for this, regarding black holes at least, is called spaghettification, because things get stretched out so much because the tidal forces are so strong. They get stretched out into little pieces of spaghetti. It's a nice little time-lapse picture. Those are always kind of cool. Oh, this is a good picture. It's a picture of a very famous nebula called the Eagle Nebula. It has some notable features in it. Here is a... Oh, I don't remember if this one has a name, but if you Google Eagle Nebula, this part commonly comes up because it looks pretty neat under magnification. This little feature here, these three little fingers, are called the pillars of creation. And just for a scale reference, these are all a couple of light years long. These little bits here. Like I think they're about 7 light years long or so. It's around there. This is just the evolution of stars, all the way to black hole. A little bit about nuclear fusion, which is what keeps the stars burning. stars. I don't think anyone can properly explain how some of the constellations got their name. This is an interesting picture. It's not, I don't think it's terribly accurate. It's just kind of neat, but what it's depicting is a binary star system, which is when two stars orbit each other. And sometimes when they get close, one star will siphon mass from the other star. As you can see, this star here is pulling matter away from this one. And that creates a bright flash because a lot of energy is being expelled from the matter impacting and getting collected from this. I'm not sure if the same principle as the accretion disk around a black hole, but I think they're similar. There's no good pictures on this page, but there's something interesting. Cepheid variable stars are, they're a certain type of pulsing star. They have very specific characteristics, and astronomers use them as what they call a standard candle, I think it is. Because if you can find one of these stars, you know a lot about it, basically. If you can find one that pulses at the right rate, you can know its brightness to a very accurate degree, which lets you know how far they are, because you can measure how bright they appear and know how bright they actually are, which basically will give you the distance. So they're very important in astronomy. This is it is, I don't know what to call it. It's not exactly famous, but it is quite well known. It's just a cluster of very bright, I think, new stars, but it's called the starburst cluster, and I think it's quite pretty. Of this is about telescopes after this section, and I'm not really going to talk about them, but excuse me. I'm gonna stop at this picture, but I'm going to talk about a couple of interesting things about galaxies. This why did my light turn off? I'm not sure, but it's still recording. I don't want to mess everything up here. You can see this though, right? Yeah, that's okay. Sorry if that's a problem. I'm still trying to work out the kinks. This is the longest time I've done a recording this long. So, this, I'm actually not sure if this would constitute a barred spiral galaxy. I don't know if this is enough of a bar, but it's a spiral galaxy, like the Milky Way. And an interesting feature about galaxies is the orbital rotation, or just the orbital velocities of the systems in it. With the solar system, and through conventional Newtonian physics, you get the sun, or the center mass in the middle, and everything orbiting it, obviously, which is what's happening here. But the closer you are, the faster your orbit needs to be in order to be stable. Otherwise you'll fall in. So that's how it works in our solar system. The farther out you get, your orbit becomes longer, so it obviously takes longer to complete, but you also actually move slower, so you take even longer to complete an orbit. What happens in galaxies is, I'm not sure if there's a curve for this, but generally everything orbits at the same velocity. So obviously still the outside parts take longer to go around, but the actual velocities are the same, which we really can't explain. What we use to explain that at the moment is effectively dark matter, because you can explain it by changing the distribution of matter, and therefore gravity, in the galaxy. Now obviously this is dark matter, we can't see it, and we can't prove that it's there, but we see the effects of it, at least. So that's one interesting thing. The last thing I want to talk about is these spiral arms. A lot of people would think that they're matter that's whipping around, and it's just condensed into these brighter spiral arms, and that's why they're there. It's just a clump of matter, and it is a clump of stars, but the stars are not what defines the spiral arms. The stars actually move through them. The spiral arms are stationary features, or at least independent of the stars. A star will rotate the galaxy, go into an arm, and then slow down, and they'll clump up kind of like a traffic jam, and then move out the other side. It's not a set group of stars rotating around. Again, I'm not actually sure if there's a good explanation for this. I think I've heard it referred to as density waves, where a density wave, which is the spiral arm, moves, but is again separate from the actual individual stars. Anyway, I think this video is probably long enough. Finally, some ASMR stuff. Tap, tap, tap. Tap, tap, tap. Okay. That's it for tonight. Hopefully I can sort out